Okay. So, we have done equation of continuity in the 3 coordinates: Cartesian coordinate, cylindrical coordinate and spherical coordinate. Of course, out of these 3 we have derived 2, that is Cartesian and cylindrical, and spherical coordinate we had shown you that what is the final form of the equation of continuity. And we also said that these relations, right from that partial derivative, time total derivative, substantial time derivative, these will be very much useful when you are also progressing towards the development of the equation of motion. So, now you are deriving, those equations will be very much required and of course, even more complicated. Now, in earlier case, what we have done in the equation of motion, we have done the mass balance. But here when you are doing the equation of motion, you have to do the momentum balance, and this momentum can be transferred in not only one way, but 2 ways. 2 ways this momentum can be transferred, right? How? One is the bulk flow, right? For example, if this is the say one fluid, of course this is solid, but assume it to be, if it is coming, so this bulk is converting or transporting this momentum to another, if this be another. But this is one, and another way is, say these are the 2, or if we assume that this fluid to be of this kind of multi layers, right. So, one layer like this can transfer to its neighboring layer, and that can transfer to its another neighboring layer. So, like that these momentums can be transferred from one layer to the other layer, if you exactly the way, if you have seen that playing cards, if you keep that bunch of playing card, and if you just give one push at the bottom of that card, then what happens, the it is not that you have to give very high, the force to be very high, just give a small force and then see that the top one has come out, bottom one has gone in, and there is a distribution of the velocity, or the cards are coming like angular one, right, in an angle, not angular, in an angle that those cards are making an angle with the base, right. So, this is how there these cards we can assume to be of each card to be one layer, and they are passing one layer to the other layer, the force which you have given as a horizontal force, and that force is also translated to the vertical one. That is why the top one has remained there, whereas bottom one has gone a little away, and they have made one like this. So, if we take this, so these are the cards, right, and you have given a force at this place, then what you will see, this card which you have given a force has gone a little away, whereas its adjacent is like this, sorry, it should have been like that, okay, and this adjacent is like that, this adjacent is like that, this adjacent remain like that, right. So, there is a distribution, there is this kind of change you can see there, no. So, that if you see in reality, in the liquid also, in the fluid also, the same thing happens. If you consider the fluid to be of multi layers, and when a force is given, this is happening to that. So, how they are changing, how they are transporting the energy, this energy is being, one we said that it was through the bulk, that is the flow of the fluid by the bulk flow, so that is being transported, and another when you are doing this, that shear, the one layer to the other layer, that is by called shear. So that force is called shear force. So that shear force is acting on the layer, and thereby as it is like this, so adjacent to this, it is being pulled, this is being pulled by that, that is being pulled by that, that is being pulled by that, whether the top one remain may be there or a slight movement. So there is a definite way of deflection you can see in all the cards. So similarly the layers are. In scientific way, what we say that we know that in the fluid, particularly gaseous, right? In the fluid, particularly say gaseous, right? There, what we are showing that what we are showing that Mike, okay, okay. So, what is in that what we have seen that when you are looking at these layers, you have read kinetic theory of gases, right? There you have seen that gas molecules can, in the kinetic theory, can move in all directions, right? Of course, they can collide also, but they can also move in all directions, and thereby they are imparting the energy from one to the other. The kinetic theory of gases is established. So many people have given many theories on that, but till now there is no such kinetic theory of fluids or liquids, right? So gas is also a fluid, but okay, in liquid there is no such kinetic theory, but more or less we assume that this may be applicable, or the deviation which you will get will not give so much that your prediction will be absolutely different. So in that case, there these molecules, you imagine that one layer molecule and next layer molecule, so these molecules are vibrating, no? So this, in that vibration, they are exchanging the energy one to the other, right? So one to the, this energy is exchanged, whosoever is having more, she is giving to the less one, that energy is exchanged, and thereby this kind of vibration we call it to be the shear. Ultimately one is dragging the, pulling down the other, and that is called the drag force, or when we are calling it to be shear force. So this shear force is also acting on that. These two types of transport mechanism is there when you are considering the momentum equation or equation for motion on the basis of the momentum transfer, right? So here simply we take the simple one, that is the Cartesian coordinate. So you take one volume element. So take one volume element, right? And as earlier we have said it to be del x, del y and del z, right? So if that to be there, then we said that the momentum will be transferred by the one by the bulk flow and another by the molecular transport. Right. So, this molecular transport, if we consider that to be, say this is normally represented here as the tau, this symbol tau is used, and unfortunately maybe in the in our slides that tau might not have come properly, it might be in place of tau t. So, but it is exactly the tau. So, tau xx at the face x and this is tau xx at the face x plus delta x, right. Similarly, one can be like this and like that, right. So, which we can write to be tau at the face zx at z and tau here it is zx, right, at the face z plus delta z, right. Whereas the third one is perpendicular to this. So, there we can write to be like this and one like that, okay. Then that can be said to be tau yx at the face y and tau yx at the face y plus delta y, right. So, other than and this is our xyz, this is z, this is x and this is y. So, other than xyz, other than the molecular, other than the bulk transport, which we have shown that other than the bulk transport, this additional one is the molecular transport, which has to be also taken care of, right. So, when we are doing it, then we do the general equation for motion is like that. Momentum balance, as we have said in the beginning, that the momentum balance is done. So, in that case we can say that the rate of momentum in minus rate of momentum out plus sum of all the forces acting on this volume element right. This must be equal to the rate of momentum accumulation. Right. So, this is the basic general equation for the momentum transfer, that is based on the momentum, the rate of momentum in minus rate of momentum out plus all the forces acting on the volume element, this must be equals to the rate of momentum accumulation, right. So, this based on this the entire development of the equation of motion is based on. So, here we can write that by convection what is coming and going out, by convection, or we can also say by bulk flow, the what we are coming, that rate of x component of momentum on face x and x plus delta x, right. So, what is x? So, this was the phase x, this was the phase x plus delta x, right. And this was the phase y and the other one was this y plus delta y, and this was the phase z and the other one is the z plus delta z, right. So, if we look at that by convection, now there are three, right, x component momentum acting on the x, x component of the momentum acting on the y, x component of the momentum acting on the z. All these three are to be considered, right. Similarly for the other. So, x component, now first let us then look into that x component of the momentum, that means momentum derived from the velocity from the velocity v, which is acting on the x direction as Vx. So, momentum arising out of that in acting on the x direction is, that is the x component of the momentum acting on the x. This we will be first finding out, and then we will go to x component of the momentum acting on the y and z, right. So, then what we can write, that x component of the momentum or rate of x component of momentum so which is acting on the phase x and x plus delta x, right. So, they are rho Vx times Vx at the phase x times its area del y del z. This is for phase x, and the other one rho Vx, right, into Vx at x plus delta x into del y del z, right. So, similarly we can also write that x component of the momentum, right, acting on the phase y and y plus delta y, this can be written as rho v y due to the x component at the phase y, this times the area, what is area, del x del z. This is for the phase y. Similarly, for the phase y plus delta y, it will be rho v y v x at the phase y plus delta y into the area del x del z, sorry, del x del z, right. So, similarly, the x component of the momentum acting on the z direction is, so z and z plus delta z, that can be written as rho v z, right, into the x component, that is V x at the phase z into area del x del y, and similarly rho v z due to x component V x at the phase z plus delta z into area del x del y, right. So, these are then all three x component momentum acting in the all three, right, what we have given. So, fluid was flowing, right, a fluid was flowing. So, the moment it has a velocity v, it will have three components, one acting in the x direction, one acting in the y direction, and another acting in the z direction. So, all these three directions we have taken care of due to the velocity component Vx or the Vx component, that how much momentum is being transported to the all three directions, that is x, y and z, that we have taken care of, right. So, both at the inlet and also at the outlet, right. So, then we can say that this was by the bulk flow. So, by molecular transport, this molecular transport, again for understanding I am repeating that molecular transport means that one we assume that in the face, in this is one plane, or we also showed that this is one plane, this is one plane, right, and that is another plane. So, these two layers when they are there, so if we assume that this to be one molecule and if we assume that this to be another molecule, these two molecules, because of this vibration of the molecule within that plane, it is not that they are going like kinetic theory of gases, what we have seen that it is going till it is colliding, right, and to the boundary. It is not like that. It is on that plane, not going, the molecules are not going away, but it is just like vibration, it is oscillating, right. In that case, this molecule, one molecule is imparting energy to the other molecule. Obviously, the one which is having more will give to the lower one, right. So, but this is happening for the flow of the fluid. Now we are considering in the x direction, right. So, that if we look at by molecular transport, if we see similar way that how it is being written or how you can write it, that rate of x component of momentum on the face x and delta x, we can write that x component of momentum acting on the face x and x plus delta x, right. So, this is by molecular transport, we can write to be equals to tau x x, right, at the face x into its area del y del z. This was for the x face, and for the x plus delta x face we can write tau x x at the face x plus delta x to del y del z, right. Similarly, x component of the momentum acting on the face y and y plus delta y, that should be equals to tau yx at y into the area del x del z and tau yx at the face y plus delta y into area del x del z. Similarly, we can write x component of the momentum acting on the z and z plus delta z direction is tau zx at z into the area del x del y, and for the other face tau zx at z plus delta z into del y del x, right. So, if we see this, we have taken all both for the molecular transport as well for the bulk transport, the total components of the x component, or rather total molecular momentum transport for the x component of the momentum in all the three directions x, y and z, right. So, velocity component Vx, that is imparting the momentum, and this momentum is acting on all three directions and in two ways, one by the bulk transport, another by the molecular transport. So, all these six, right, three for the bulk flow and three for the molecular transport, that we have seen how they are acting for one component, that is velocity component Vx, right. We can then say that sum of the convective and molecular terms, if we write, they will be rho Vx at into Vx at x plus, or rather minus rho Vx at into Vx at x plus delta x, right, into the area del y del z plus rho Vy into Vx at y minus rho Vy into Vx at y plus delta y times the area, that is del x del z, right, plus rho v z into Vx at z minus rho v z into Vx at z plus delta z, this, right, plus this times the area, area is del y del x, right, del y del x, and this is for the all three terms of the bulk transport, and for molecular transport we can write that tau at xx at the face x minus tau at xx at the face x plus delta x times the area, that is del y del z plus tau at the face yx at y minus tau y at the face y plus del y times the area, that is del x del z plus tau zx at the face z minus tau zx at the face z plus delta z into del x del y. So, into del x del y, okay, right. So, these are all the forces acting, not all the forces, rather this is for bulk and molecular transport, right, bulk flow and molecular transport. So, this is said that tau zs, that is x component of the molecular transport acting on the z direction, right, x component of the molecular transport acting on the z direction, x component of the molecular transport acting on the x direction, x component of the molecular transport acting on the y direction. This is how this is interpreted. This we have to keep in mind. Subsequently, when we will also find out that this tau can also be expressed in terms of viscosity, right, from the basic definition of viscosity, then we also will see that there the velocity component and the direction both are acting together. So, here as we said in tau yx, tau zx, tau xx, these are x component of the molecular transport acting on the respective directions of x, y and z, right. So, other terms could be pressure force, that can be written as P at the face x minus P at the face x plus delta x into the area, that is del y del z. Then this is all for x component, and gravity forces acting, which is rho times Gx times del x del y del z, right. Rho is kg per meter cube, this is a meter cube, so that is why this has come. And accumulation, we can write accumulation of the x component of the momentum, that we can write del T of rho Vx, right, del T of rho Vx into the volume element del x del y del z, right. So, we have done in this class till till now that how the molecular transport and how the bulk transport we can formulate it in terms of the components of the rather velocity components individually acting on the different coordinates, that is x, y and z. Of course, we have taken Cartesian coordinate, right. So, as we said that this will take long time, this is not a small one, and that is why we have taken the easiest one, or the one which you can handle easily in the that is the Cartesian coordinate, and we have done up to that molecule accumulation of x component momentum accumulation, right. So, next we will sum it up. Sum means we will go for the other two, that is y and z component, and then look into the total and finish the entire thing as the equation of motion known as the, which we said Navier-Stokes equation, right. Okay, thank you.